All right, good morning. In this video, we're going to talk about linear momentum. We're going to do a practice problem on a missile. I'm going to show you on paper and then show you a octave code that will solve for the velocity, all right, as a function of time for the 4 seconds that these rocket boosters on this missile are engaged, okay? Take a look at the videos above that talk about linear momentum, that talk about angular momentum, to give you an idea of what's happening, okay? All right, let's get started here. All right, so here we have a missile that weighs 40,000 pounds. The constant thrust provided by the turbojet engine is 15,000 pounds, okay? Then we're getting additional thrust by 2 rocket boosters B. The propellant in each booster is burned at a constant rate of 150 pounds per second with a relative exhaust velocity of 3,000. If the mass of the propellant lost by the turbojet engine can be neglected, okay, determine the velocity of the missile after the 4-second burn time of the boosters. Initial velocity of the missile is 300 miles per hour. So we're ignoring the mass of the propellant of the turbojet. However, we're not ignoring the mass of the of the booster's propellant, okay, of that flow rate. All right, so we're gonna account for that. All right, so what we have givens. We got the weight, 40,000 pounds. Thrust of the turbojet engine, 15,000 pounds. Okay, M dot E is 150 pounds per second. The relative velocity of the missile with respect to the exit, right? Where does it say that? Relative to the exhaust velocity is 3,000 feet per second. Initial velocity is 300 miles per hour. We have a sketch here. I'm just going to draw the rocket here. Then we have thrust. We have drag force. And then we have these boosters which shoot out a relative velocity. And you have to use relative velocity in these, okay? Because this rocket is, or this missile is moving to the right, but the exhaust velocity, all right, we're going to do it based on the object being on the missile. So we have to use a relative velocity, okay? All right. So let's find V as a function of time. Okay. All right. Solution. We're going to find a few things first. So let's find ME, the exit flow rate. ME is going to be 2 times 150 pounds per second, because there's 2 of these, times 1 over 32.2. This is a conversion to slugs, okay, because you got to use slugs, slug per second. So that's your English empirical unit for flow rate, okay? We need to find the initial mass, and we're going to use W over 32.2 again to get this into the correct units. 32.2. This is 1242 slugs. Okay, that's the mass equivalent in empirical units. Now we're going to find M, the mass of the missile, as a function of time. Okay, because the propellant of the rocket boosters are leaving. We're going to assume a linear fashion. So if we start with the initial mass of the rocket and we subtract the mass flow rate times t, right? This is kilograms per second, and this is time. This is seconds, so that'll give us kilograms. This will tell us the mass of the missile as that fluid is being ejected. Okay, now for the linear momentum. We're going to use Newton's second law, or linear momentum, which states the sum of the forces equals m times a plus summation of m dot v out minus summation of m dot v in. Okay, now let's put some notes over here. We know that ma, this is inertia, right? Inertia force. This is kilograms. This is meters per second. This gives us a force. Okay? All right, so that's 1. That's 2. M dot times V, that's your momentum, linear momentum. Okay? This unit is kilograms per second. This is meters per second. And guess what? We get kilograms meter per second squared. That's another force. Okay? So the way we write it is this way, and you're going to realize that the way we write it is actually, this is how you write it, out minus in, and these vectors v have a direction. You're going to realize that this rocket booster thrust is going to give us a thrust, eventually I'll show you here, that shoots to the right. Okay? So think about it like linear momentum. Anytime you have your hose in your shower, right, you have to hold it. It shoots the water out. That mass flow rate times velocity of those water jets would equal the force that you're holding that on, right? So you're holding that force. You're holding that shower head from flying backwards because of the m dot times v, the linear momentum of the fluid. So what we need to do, and if you notice, I labeled forces, and then these are the linear momentum terms. Okay? So if you want, you could have put m dot times v to fully put forces. So what we have is, let's only do the x direction. Assume that way is positive. So we have thrust minus drag equals, I'm going to put m dv dt, okay, plus we have out terms, right? So because I've combined the mass flow rate to be 2, I'm just going to say that it's m dot e, and then we have to put in a negative relative velocity, okay, because this velocity shoots backwards to the left. And because the missile is moving and the exhaust is moving, we use a relative velocity in these linear momentums, okay? And then we don't have any fluid coming in. There's no fluid at all, okay? Yeah, we have air, but we're talking about like that's accounted for the drag here, okay? All right, you're overcoming that air, okay? So that's actually included in this drag force, okay? So there's no other like fluid or air coming in, okay? Yeah, there is air coming in the turbojet, but we're not worried about that. We're only looking at these rocket things, and they only have flow going outward, okay? So let me just rearrange this. So we get T, I'll put the drag force, 1/2 rho v squared CD times A. I'm going to move this over, plus m dot E VDE equals m dv dt. Okay, now look, see how this is now adding to this thrust phase? which it should, right? Okay, it's shooting out left, but it's helping it propel to the right. So that thrust phase, this is kind of like the thrust of the rocket boosters. Okay, this is the thrust from the turbojet engine. Okay. All right. One more time. 1/2 rho v squared CD A plus m dot E v dE equals, I'm going to plug the mass equation that we had in at the top, m naught minus m dot E times T times dV dt. And I'm just going to solve one last time for the acceleration, because we're going to numerically solve this, okay? And I'm going to show you. Okay. So what we can do is we can solve this numerically. What do I mean by that? Well, we're going to basically plug in T, rho, some velocity, a drag coefficient, an area, mass flow rate, your relative velocity, and this at different times. We're going to start at time 0. We're going to pick a delta t of maybe 0.1. Okay. We're going to start with initial velocity of 0. And what we're going to do is we're going to march forward in time. So maybe time of 0, velocity is 0, okay? And we can then find our next velocity. How? Well, if we know this, if we plug in some initial stuff first, we'll have acceleration, which is dV dt, right? Okay. Well, on the top, you can kind of switch it like this. This is v2 minus v1 over a delta t. So if we have a, right, and that's all of this stuff, then what we can do is we can solve for our next velocity. If we know our previous velocity, we know a, which we can calculate initially, okay, and we multiply by our determined delta t. And then boom, okay, we can now find v2. We then plug that back in to find our next acceleration, right? Okay. And then find our next v3, which would be v2. This would be a2 times delta t. And we just keep going forward and forward in time, okay? So let me show you that code. Let me go to this, and let me bring this up right here. And I don't know if this is going to fit, but that's okay. We can do this. Oh, sorry. Okay. All right, let me make this a little bigger if I can. Maybe. Okay, I can do that. I think you can see that okay. All right, so up here we have our givens. W, T, mass flow rate, relative velocity, and initial velocity I just converted to miles per hour to feet per second, okay? Then we have the density in slugs per feet cubed. We have CD. I picked a diameter of 6 inches. You just found the area. I have a delta T. And then my end is 4 seconds, because that's how long we're running it for, okay? Now, how can I... Oh. Let me reset and click on this. I'll have to do this. For some reason it disappears on me. Let me move this over. There we go. Okay. Here's calculations. Mass flow rate converted to slugs. Initial mass converted to slugs. Now here is the big chunk right here. So here is initial condition. Time of 0. Initial velocity is v naught. right? That was the miles per hour to feet per second. And what I'm going to do is I'm going to do a loop for 4 divided by 0.1 so we can get to 4 seconds, okay? So this gives us the number of times that we have to do 0.1 to get to 4 seconds, okay? Here is the mass at any time of that interval, right, is m naught minus the mass flow rate times time. Okay, this is the mass of the missile. Here is the drag force, the 1/2 rho v squared cd times a. And you see how I have a parenthesis I here because that's the drag force depends on the velocity, and the velocity of this missile is changing, right? Here's the thrust of the rocket boosters, right? The mass flow rate times this, and this is always constant. This isn't changing in this particular problem. Here is the acceleration that I solved for as a function of time, right? We have an I, which is the thrust of the turbojets minus the drag plus the thrust from the boosters divided by the mass. So this is our acceleration. If we multiply this acceleration by our delta t, right, this term right here, and we add it to initial velocity, we get our next velocity. That's why it's I plus 1. Down here, this is t of I plus 1. Our next time is our previous time plus a delta t. What's going to happen is it's going to calculate v of 2, t of 2, and it's going to go all the way back to the top, recalculate all of this stuff. Find your next acceleration, find your next velocity, and so forth. It's going to keep doing this until we get to 4 seconds. Then what I can do is I can plot. I can plot the velocity as a function of time. I can plot the drag force and the thrust of the rocket boosters. If you notice, I had to put this in 1 to n minus 1 because in my loop up here, I'm only calculating FD of I and this of I. Where down here, this is I plus 1. So these velocities and time will actually have an extra term. It'll be, say, 101 instead of 100. So you just have to realize in your coding that you did that. Excuse me. So this is how you would write this code. This is a numerical method of marching forward in time. I like to do this because it's kind of easier to solve than trying to integrate. So let's take a look at the graphs. So here is, again, sorry, but this is velocity on the y, time, and then you have this blue line here. Let me change this to white to make that easier to see here. Give me 1 second. And let's do line width of 2. And I'll make this on every single one. I'm not sure why I'm getting black graphs in Octave, but I don't know, it's free. Okay, there we go. All right, so here we have velocity versus time, 4 seconds, and we get about 580 feet per second. Okay, starts at 300, or it's 300 miles per hour, whatever that converts to feet per second, and we get a linear line going up. Okay, now I put in, if you notice, I had this commented out because I took the drag force out. And when you calculate the drag force, it's nothing compared to those thrust forces. So you're like at 4 seconds, I'm getting 35 pounds. And when you look at the thrust of 15,000 from the turbo and the 28,000 from this rocket boosters, this drag force is nothing. So you could technically ignore this because it's not playing a major role in calculating the velocity of this missile. Okay, so I just wanted to show you that. That's pretty cool. Sometimes you can make your assumptions. You realize, okay, we have tons of thrust. This drag force is nothing. You can just ignore it and assume that you ignore it. Okay. All right. So let me go back to this. Go back up here. So in this particular problem, I used linear momentum to find velocity as a function of time. And then we solved it numerically. All right, thank you. If you have questions, let me know.